Okay, functions and data analysis fans, our topic for today is Notes 1-4, Simplifying Radicals. And this is a review of Algebra 1, but we're also going to get into some Algebra 2 concepts as well. Before I start the notes here, let me tell you your joke of the day. Why don't cannibals eat clowns? And the answer is because they taste funny. All right, the first thing we're going to do here is talk about perfect squares and square roots. What does it mean to be a perfect square? So for the first perfect squares, we're going to do the first 12, from 1 to 12. When you raise a number to an exponent, that exponent tells you the number of times that you're multiplying the number by itself. So 1 squared is the same as 1 times 1, which is then equal to 1. 2 to the second, or 2 squared, is 2 times 2, which is equal to 4. 3 squared is 9. And 4 squared, so we don't need to keep writing down 4 times 4, 5 times 5. So 16 and then 25. 6 times 6 is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 times 10 is 100. 11 times 11 is 121. And 12 times 12 is 144. Why do we use the term squared? Why do we say 3 squared? Well, the way that people used to think of this in ancient times, they didn't think of math in terms of symbols, they thought in terms of visuals. So 3 squared was actually a square of 9 dots. So why is 9 a perfect square? Because I can arrange them in the shape of a square. 16 is a perfect square because I can take 16 dots and arrange them in a square where the sides are 4 by 4. So 4 in the row and 4 in the column. So literally, when we say that a number is squared, it means you can write this in the shape of a square. You can draw it out. The other thing that happens, there are some nice patterns here. If you think about how do we get from 1 to 4, now these are the perfect squares are the numbers 1, 4, 9, 16, 25, and so on. These are perfect squares. Well, to get from 1 to 4, I add 3. To get from 4 to 9, I add 5. 9 to 16. 16 to 25. Notice that each time, to get to the next perfect square, we're going up by an odd number. The next odd number after 9 is 11. 25 plus 11 is 36. Now, it's a kind of a neat pattern. Are you going to use it a whole lot? Not particularly. I mean, if you say 121 to 144, I would add 23. If you were trying to figure out 13 squared, well, you would add 25. And 144 plus 25 is 169. So, I mean, you could use that pattern to keep going. That's probably not the easiest way to do it. All right, so we have our perfect squares are all these numbers. The square root of a number is basically the inverse process. In other words, instead of squaring a value, if we undo that, we get back to where we started. We take a square root. The square root of 1 is 1. What was the number that I started with? That's what a square root tells you. The square root of 4 is 2, because 2 squared gave you that. So if I take a number, if I take 3 raised to the second, and I get 9, but then I turn around and take the square root of 9, I get back to 3. So the square root undoes the square. It's kind of like if you do 2 times a number and then you divide by 2, what happens is the 2's basically undo each other. Okay? Square root of 9 is 3. The square root of 16 is 4. So when I take the square root, I'm getting, for these integers here, I'm getting the original number that I was squaring. The square root of 36 is 6, and you can keep going. The square root of 100 is 10. 121, the square root is 11. 144, the square root is 12. Okay, and you can write down for 7, 8, and 9 as well. So a square and a square root, again, what they're doing is they're undoing each other. Okay, so they kind of reverse the process. Now what it means to simplify radicals, and this is our main topic for today, simplifying radicals, the radical is this symbol. Now most of the time you look at it as a square root, but it could also be what we call a cube root, a third root, it could be a fourth root, it could be anything else. But to simplify a radical means to pull the perfect factors from the radical. Pull the perfect factors from that square root symbol or cube root symbol. Now I'm going to explain what that means here in a second. Directions, let's do some examples. Simplify the following radicals. Well, let's say we have square root of 18. Now if I look at my list of perfect squares, notice that 18 is not on there. It's between 16 and 25. So the square root of 18 would be something between 4 and 5. And if I take the calculator and if I go second and then the x squared key, and I can type square root 18, and what we get is a decimal. We get 4.24. Well, when you simplify, we're not going to leave it as a decimal. That's not simplified. So what we are going to do, though, is we're going to break up 18 with a factor tree. Well, 18 is 2 times 9. 2 is a prime, so I'm going to circle that. 9 can be divided by 3, so 3 and 3 are the factors, and now we're done. What I'm going to do is this. I'm going to rewrite the square root. Instead of writing the number 18, I can write it as a product of prime numbers. A product of primes. Product means to multiply, and these are all prime numbers. Now, if you're ever unsure whether this is correct or not, if I do 3 times 3 times 2, it should give me 18. And it does. So what that tells me is that I have factored this correctly. Now what I'm looking for here, the definition of simplifying radicals, is to pull the perfect factors from there. In this case, a square root, a perfect square is a number times itself. 4 times 4, 5 times 5, 6 times 6. In this case, 3 times 3 is a perfect square. Now, 3 times 3 is 9. I'm not going to write that as 9. I'm going to keep it as this pair of numbers. But if you think about it, the square root of 9, let me come back here, the square root of 9 is 3. So I can actually take the square root of this 9. Now what happens, I'm going to pull that out. When I have a pair of numbers that are the same, I'm going to circle them. I'm going to take the square root of that pair, and what's left on the outside is just a 3, because the square root of 9 is 3. So when I pull out a pair, I write the number one time. Now you'll notice there's another number under there. There's a 2. Well, there's no other 2 with it. I can't take the square root of 2. It's not a perfect square, so I can't pull that out. So the 2 will stay under the radical symbol, the square root symbol. The 3 will be outside. My answer, simplified, is 3 square root 2. And just to show you that this is correct, the square root of 18 was 4.24. If I take 3 square root 2, and that means 3 times square root 2, we get the same value. So what that means is that 3 square root 2 is equivalent to square root of 18. The only difference is this is simplified. So 3 square root 2 is a simplified answer. So that is simplified. And the way we read this is 3 square root 2, or you could say 3 times square root 2. We don't put the times symbol there, but it's kind of like if you have 4x, that's 4 times x. Same idea here. Okay, I'll cross that out. That's just something different. Let's take square root of 108. So factor tree, what goes into 108? Well, that's an even number. because the 8 is even, the last digit, I can divide by 2 and I could get 54. 2 times 54 is 108. 2 is prime, so I circle it. 54 is 6 times 9. And there are other ways to factor these numbers. So if your factor tree is different from mine, it's okay, but at the end, we should end up with the same values, okay, the same primes. Now in this case, we have more primes. We have 2 2s and we have 3 3s. Now I'm writing all of that. 2 times 2 times 3 times 3 times 3 is the square root of 108. Okay, or is 108. So this is okay. Now what I'm looking for are perfect square factors, perfect factors. Well, anytime I have a number and itself, that's a perfect square. 2 times 2 is 4. So what I'll do is take the square root of 4 and I get 2. And the 2 is on the outside because I've simplified it. 3 times 3 is 9. The square root of 9 is 3. Now in this case, we have more than one number on the outside. What we'll do, if you have more than one on the outside at the end, you're going to multiply that together. 3 times 2 is 6. And if anything is left over, we still have that 1, 3, but we can't pull it out because that's not a perfect square. The answer is 6 root 3. And that's as far as we can take it. In number 3, let's go ahead and do that. 7 times the square root of 80. So to start this, we're going to ignore the 7. We're going to leave that where it is. Let's do a factor tree for 80. So I'll say 8 times 10, and then 8 is 2 times 4. 4 is 2 times 2. I always break it down into just prime numbers, and 4, because I can divide it, I keep going. 10 is 2 times 5. Both of those are primes. So on the side here, we have a 7 on the outside. I'm going to rewrite the number 80. That would be 2 times 2 times 2 times 2 times 5. Now to simplify means to pull out the perfect square factors. Anytime I have a pair, that's a perfect square. So we have a pair of 2's. That's really 4. Square root 4 is 2. So that comes out. Here's another pair of 2's. That's a 4. 2 times 2 is 4. Square root of 4 is again 2. Now on the outside, we have 2 times 2 times 7. So we're going to multiply that together, and that would be 4 times 7 is 28. We still have a 5 underneath. So our answer is 28 square root 5. When you simplify, what you do is you break it down, but you don't change the value. So if I type the original problem, 7 square root 80, and hit enter, and if I type my simplified answer, 28 square root 5, I should get the same value, and I do. So even though this looks different, they're the same value. That's what it means to simplify. So we're going to stop there. That's the end of part 1. Go ahead and click on part 2, and we will continue.